Restart.
First, let me thank the organizers for giving me the opportunity to present our work. My topic is engineering surface critical behavior of quantum critical points. My name is Wenan from Beijing Normal University. These are my collaborators, Chen Xiangding from Anhui University of Technology, and Long Zhang from Carnegie Institute for Theoretical Science, University of Chinese Academy of Sciences. Our paper has been published. Here's the outline of my talk. First, I'll give introduction using this, discussing classical surface criticality. Then I'll move to surface criticality of quantum critical points. Namely, I will discuss three surface transitions: ordinary, special, and extraordinary. Then I will give conclusions. So I will realize that I will talk for 1 hour. So maybe that's more than enough. So maybe I'll have chance to talk the second part, which is of my talk. There will be random singlet phase in disordered two-dimensional quantum magnets. For here's a classical model. We think of 3D Ising model. Hamiltonian is like this. You have bulk part, this Ij, bulk spins, and you have a surface part, this PQ, surface spins, and they couple together. This surface bulk coupling part. And here's the phase diagram. So if this surface coupling is comparable to bulk coupling, then the surface remains disordered at bulk Tc. This is understandable because the surface surface spins have less coordinate numbers. So here is the so at bulk Tc, the surface singularities are induced by the bulk criticality. So this situation is called the ordinary transition surface.
Yeah, question. You SI, capital SI, is an Ising spin or Heisenberg spin?
Ising spin.
Just a single component.
Yeah. Maybe you should not use.
But the Hamiltonian is defined on a 3D spatial system.
It's a 3D model, but with open boundaries. So you have a surface. But in the case Js is much larger than J1, so the surface undergoes 2D phase transition at a temperature. We call it Tcs, much higher than the bulk critical temperature, Tc. So when you lower temperature, the surface order first. If Js is much larger than J. So in this case, at temperature Tc, the surface exhibits extra singularities, which is called extraordinary transition here. So surface is already ordered, but still you can detect some singularities there. When the surface TCS and TC merge, can merge at a fine-tuned surface coupling strength, JS star, like here. If you scan this, fine-tune this JS to a special value, JS star, then both 2D surface and 3D bulk are critical. This is a multi-critical point called special transition. So this is the phase diagram of this simple classical case.
Excuse me. What do you exactly mean by when you have an ordinary transition and you say that the boundary is disordered at the critical point, because the bulk is also has zero order exactly at the critical point, right?
Yeah, but it's critical.
Okay.
Yeah, where correlation length is infinite.
Okay. I see.
So if you measure I will come to this.
Okay.
But Wenan, can you tell us about what are the universality classes? So in the bulk it's a 3D Ising model.
Yeah.
But if you measure correlation functions on the surface.
Yeah, here. I will come to this. Yeah.
But in the phase diagram you had before, you go back to that.
Yeah. Here you have ordinary universality class. Here you have an extraordinary one, and you have a special one. You have 3 of them.
And a surface. So the surface one is just the 2D.
Surface one is 2D icing. Yeah, that's we make the bulk TC. Then you measure the surface. It's different from the here.
I see. And the ordinary is the 3D Ising model?
Ordinary
Yeah.
surface. No. It's something in addition to 3D icing. So let me discuss the free energy. You will be more clear. Here, the total free energy can be written like this. This is bulk free energy density. This is volume, and this F1 is the surface free energy density. S is the area. So this bulk free energy density satisfies this finite size scaling relation with analytic part. This is the singular part. This is the surface free energy. You see, in addition to the temperature and magnetic field, you have T1 and H1. Those are surface scaling fields. So this is different from the bulk. So you have 2 additional relevant scaling fields in addition to T and H. So this, let us look at observable surface susceptibility, defined as this different derivative to H1, this is so-called surface scaling field. Then, from this finite size scaling of free energy, you can find this relation. So this is surface susceptibility with this scaling to YH1 minus D plus 1. This Yi is irrelevant exponent. This is Y sub T So, and there's a contribution of analytic part of free energy. So if you study the ordinary transition, that means you simulate the system at a given Js comparable to J. I mean, like here, any J, any Js. Then you can find this chi1 is a constant plus a power law. And we can find this exponent yh10, which has this value. And this yt1 is irrelevant. But if you scan Js, like Dan Blatt, Nightingale did in this paper, they use a different symbol, but essentially this is Js. You change Js, and you multiply this, move this part to the right, then you have this exponent, and they have a well-defined crossing point, indicating that there is a special transition. And this value gives you a y sub h1 special transition, 1.636. And you can find from the slope of these curves, you can find this y sub t1 special. This is the universality class of special transition.
So in this case, they have somehow subtracted out the constant there?
In this special case, there's no constant.
Oh, okay, that's really
Yeah. Yeah, this constant only for the ordinary. Yeah. Okay, this is the classical picture of surface criticality.
So what are these T1 and H1? So they're also even odd and even under Ising symmetry?
Which one?
YT1 and YH1?
Oh, this one?
Yeah, those two operate.
No. This something like you can think it's Js minus J. It's additional.
So that's YT1. And YH1 is
Oh.
similar when you break them.
You mean YH1?
Yeah.
Well, this is something like a field, like a magnetic field breaking this Ising
So if I
symmetry.
put H and H1 to 0 and T and T1 to 0, then I'm at the special point. Is that correct? If I put all the H's to 0, so
You put this to 0,
and
not YT1. Yeah.
no, T1 and T.
T1. Yeah, exactly.
That's the special.
Yeah.
That's the special.
Yeah, that's right. So that is a fine-tuned point. Yeah, that those 2D critical line meet the 3D critical. So this is the classical model, and we can also study the correlation functions like this on surface S111 to 1 plus, this is x plus r. So the two surface spins have as a distance r. Yeah, this C parallel r. And we can also, sorry, I didn't, this is wrong, should be here. This C perp is the surface spin correlate to a spin deep in the bulk, so it's vertical. So and we expect this kind of power law at this critical phase. So we actually this defines the eta parallel and the eta perpendicular. So you can think this as a surface scaling dimension of the surface spin, and according to a very simple dimension counting, you will find this scaling relation, because this surface spin, the scaling dimension of surface spin plus this magnetic scaling dimension of magnetic field, surface magnetic field, should be the dimension of the surface. So this gives you this relation. And if you count this scaling dimension as the sum of surface spin and the dimension of box spin, which the box spin has this well-known scaling dimension, then you have this relationship between eta parallel and eta perpendicular perp and eta bulk. So these are two very important scaling relations of those surface exponents, scaling dimension.
Oh, so I just want to make sure. So for these functions, you are measuring it at the extraordinary transition point, right?
This applies to every case. We measure it extraordinary, ordinary, and special.
Okay.
Okay. This is just in any case you can have exponent, but different.
I'm sorry, I got lost. So what is the difference between perpendicular and parallel? They're both surface correlation functions, right?
Oh, no. I mean, you have a surface. This is bulk. You have a periodic boundary in here, but here you have a surface open boundary. This S1 to this SR is surface correlation. This S1 to here SR is the C pop. So two directions. This is the surface. See, this is the Z direction, and X, Y direction are periodic boundary conditions. So you have two exponents. So surface critical behavior also sets in at quantum critical points. In this work, we actually studied the surface critical behavior of the dimerized spin half anti-fermatic Heisenberg models on the square lattice. So we realized all three types of surface behavior, critical behavior of 3D03 universality class by engineering the surface configurations. This is somehow a surprise, because you know in 3D classical 03 model, the 2D surface has no symmetry breaking phase at finite temperature, according to Wagner theory. So, but we can realize this 3D 03 universality class surface critical behavior of 3D 03 in a quantum system. So that's a little bit surprise. So here's the dimerized familiar Yeah, everybody here, I'm sure, familiar with this dimerized spin-half Heisenberg model. You have J. Here is the weak bond. You have a strong bond J prime. This is a columnar dimerized model. This is a staggered model. And this figure I steal from Anders' slides. So if J prime and J are comparable, so the system is in a near state. When J prime over J becomes large enough, a spin gap open, and the system becomes gapped, dimerized phase. So it is ordered phase. And this transition is 3D03 universality class. For columnar case, critical point is 1.9096. But for this staggered model, the critical point is 2.5196. And there was a debate on the universality class of this model, and this was resolved by this paper. Because this is due to there are two competing irrelevant fields, makes the life difficult, right? To find out the real universality behavior. And okay, actually what we did is cut the models in several ways. See here we cut this columnar model this way, we called cut 1, and the stagger model this way, cut 1. And also cut 2 means we cut strong bonds. Here also we cut a strong bond. So by this way, we can realize the three types of surface critical behavior.
So for this Hamiltonian, you can have two different dimerized phase, right?
No. Yeah, detailed, because this is explicitly breaking. I mean, this dimer pattern decided by this Hamiltonian, right?
Yes. So you have two different.
Yeah,
dimerized.
that's true. Yeah.
You should not really call it even ordered phase. I think you mentioned that the dimer phase is an ordered phase, but it's not really because...
No. Dimer phase, dimerized disordered.
Disordered phase.
Disordered, yeah. Maybe by mistake.
I heard it wrong.
Yeah, disordered. So the Monte Carlo method we use Anders' projective quantum Monte Carlo algorithm with valence bond sort basis, and in this case we measure this surface magnetization squared. This quantity behaves like susceptibility, surface susceptibility in a classical case. So we expect there's a constant and a power law part. This D is the space-time dimension. It's the space plus Z. Z is 1. And so this actually capital D is 3. And we also measure this parallel correlation and perpendicular correlation function, and actually to find these two anomalous dimensions. using this quantity, we can find, we can estimate YH1, which is the scaling dimension of the surface staggered magnetic field. Okay, this is the scaling dimension I mentioned in the class in the introduction. So, okay, now the calculation. First, we started cut 1 case. So the surface cut 1 in both models do not break any strong bonds. So this, so the surface states remain gapped in the bulk disordered phases, because it just it didn't break any strong bond. So this is just like the classical case that surface disordered. So if you measure this susceptibility like quantity, you can see this is 1 over L. It converges to a finite value C. And we can estimate, and it can, and this power law decay, power law relation gives you Y sub H1. And this is for the blue ones are for columnar case, red are for staggered case. And and this is a log plot for C parallel and C parallel and C perp. And yeah, and you can see a very good power law behavior, and we can estimate eta ordinary and eta perp ordinary. And these exponents are the same within the error bar. So they are in the same universality class. And they satisfy the scaling relation I just mentioned. This one. So this is nothing so interesting, because it's just like a classical behavior. The different thing is that we didn't adapt this coupling in the surface. We just simply cut the system, like engineer, right? So this is, yeah, different, like different from the classical model, where you need to adjust or adapt this JS.
But doesn't it mean that you just happen to see that some
Yeah. You can
also in the classical case, you know, depending on what JS is, you can also not adjust anything. Right?
Yeah, you can have such a.
So I'm not sure why one case is engineering and one case is not engineering.
I will show you later. Okay. Yeah, this is. One fact I also wish to mention that these two ordinary cases are belong to the same universality class. Also indicate that 3D classical models are actually 3D O3. I mean, they are both the staggered model and the columnar model. Yeah, the bulk transition is a 3D O3. Okay, and this, okay, I'm wrong, made a mistake. These numbers also agree with classical simulation. Yeah. Then and other tests, they already measured it in 3D O3 model. And also match this field theory calculation, RG calculation of 4 minus epsilon or 2 plus epsilon calculation. So this is ordinary transition.
Why do we not observe the effect of this irrelevant field? I mean, you mentioned that there was some controversy about the nature of the universality class. I mean, before, for this staggered problem case. And if I remember correctly, it was due
this one.
Yeah, it was due to some, irrelevant field, but still the effect of this irrelevant field was surprisingly big or whatever. Do you
No,
remember
you
this
didn't
other-
read our recent paper, maybe.
Yeah, so the original proposal, which I don't know if you were involved, but Todo and others here, and some Germans.
Still Bessel was also.
Yeah, exactly. So then the original proposal was that there's the leading scaling correction is somehow different and the scaling dimension is much smaller, so the effect is bigger. Actually, what we found is that that's not the reason. The reason is that there are two scaling corrections that have different signs, so they lead to some non-monotonic behavior. And actually the exponents that were claimed in those other papers is actually wrong, because they get some effective exponent that is the consequence of two competing scaling corrections that have some completely different values of the exponents.
Yeah.
And it also depends a lot on what quantities you look at. So, it looks like in this surface calculation, maybe you don't see those competing effects, because it's not like the competing effects even appear in all quantities.
We didn't reach that system size. Or in this paper we reached. Yeah, it's just a support, but not a proof.
So you're saying that in these two cases in the above, they have exactly the same irrelevant operators, but there was the other paper.
Well, the one in the staggered model has one additional irrelevant operator, but it's not the leading irrelevant operator as was claimed in the previous papers. It's actually the second one, but it has a different sign, at least in some quantities that people have looked at.
But that depends on the model.
It depends on the model and the quantity you look at, but sublattice magnetization and speed stiffness and so on actually have non-monotonic behavior because of this competition, and you only see that if you go to really big system sizes.
I see. So my question is, why didn't you see such an effect in this?
Yeah, that you have to ask Wenan, because I have no idea.
What?
As you said, in some other cases, this effect of this irrelevant scaling field was visible. But,
But you see the difference is in many decimal number away, right?
I see.
Not really.
Maybe you don't have it in the surface exponent.
And also it depends on the prefactor of the irrelevant or corrections to scaling. Sometimes it is important, sometimes it's not. But I don't know, I'm not sure. Yeah. But in our case, we didn't see any difference.
Yeah, but I think it's a good question. Why?
Yeah. Okay, now I comes to the why we call it engineering, and this is a question. Because in this case, in the columnar model, if we cut this way, then we make the system at exactly the special transition. So it's not a fine tune, just cut the strong bond. So this is proven by these two plots. So first we see this quantity converge to 0. So the constant term goes away, and we this is log, and we can find out this special this exponent for spatial transition, and also this C perp and the C parallel has give us this eta, this 2 eta, and all these are here, and they satisfy the scaling relation, and they are different from the ordinary value.
So is it because you always have like an effective spin 1/2 chain there, and that's always critically independent of coupling?
That's right. Yeah, that's the reason. So, oh, sorry. Yeah. Where is it? Yeah. Let me go this page first. So this spatial transition was first. It was never anticipated in a 3D classical model, right? Because we don't have Morbin Wagner. There's no long-range order, so you cannot fine-tune such a transition. And even more important, this phase, this critical state has a pure quantum origin. It's the topological theta term of S12 antiferromagnetic Heisenberg chain, yeah, that which suppresses the topological defects and leads to the critical state. So simply speak, the dangling bonds form a Heisenberg chain, 1D Heisenberg chain. It is a gapless critical state. So you don't have to adapt the coupling. Just the cut makes the edge to be critical. Okay, and this is similar to the early study of this model. This is, they call it decorated square lattice. So if you adapt this J prime and J, you can have, when this J is very strong, you can have plaquette valence bound solid state. And when it's comparable to J prime, you have neo spin half neo state. If J prime is much larger, you can have this AKLT state. So at this, I think it's this critical bulk, the bulk critical point, you also have a special surface state, critical state, which has the same critical exponents as what we have here. So originally they think this is the result of bulk topological state. It's edge effect of the bulk topological state. But now we believe it's just a general consequence of the coexistence of the critical states both in the surface and the bulk. Yeah, if you have a simple surface which is gapless and the bulk is gapless critical, you have this surface special transition. Yeah, and this is robust news.
I was a little confused. So if you don't have to fine-tune the value of JS, what is the modified phase diagram?
This is just I wish to show you that we are here. That doesn't mean I need to adjust some JS. This is just to remind you it corresponds to the classical picture.
But there must be some more true phase diagram then.
Oh, then no, there's no.
Oh,
Just
really?
the boundary condition.
But of course, you can still tune J over J prime in the bulk and write down
Okay.
a phase diagram. But I guess
Okay,
the
then
point is that
something
you-
like here. This is the
Right.
G, right?
Exactly.
You have you
I
add
see,
it
I see.
at the
But then the
GC.
difference is that above TC in the corresponding classical quantum model, you always have the critical correlations of the Heisenberg chain in the edge, right?
Yeah.
Whereas in the classical case, it's a completely disordered phase at high peak.
Yeah, yeah, yeah.
Isn't that
So
right?
it depends on where you cut, then you set. So you imagine this phase in quantum case is the, okay, I should stop. In quantum case, it's this part. High temperature match this. Low temperature is nil.
Okay.
Then you set it here. But if you cut here, you get the ordinary. If you cut here, you get special. And I will tell you, if you cut here, you get extraordinary.
I see.
So. And okay, now
By the way, I did also confused. Your two different dimerized phase, both these dimerized phase are also next to the near order phase. Is that true?
yeah. It's two models, right?
No, but the critical coupling constant you gave in previous is quite.
It's different.
Yeah, no, the previous one. Yeah, this one.
Yeah,
You see, J prime over J is
different.
1.9. It's different.
Yeah.
But the staggered dimerized phase are not near to the near order phase. Right?
They are, if this phase, this is staggered one, right? This is new.
I think they're two different models. It's not
Yeah.
this J prime and J is being tuned into
Yeah. If you,
This
I
is
didn't,
J prime and J double prime. So
I can also give you a similar phase diagram to this model, right? You still have this,
A different Hamiltonian. You have a two different.
right.
But here just to sit.
Same one, but you see, sorry. But you see this J prime has different locations, right? Here and here.
I see.
Same
I see.
formula,
So
but
different
different
model.
meaning. Yeah,
Different
that's two
model.
models. Yeah,
Yeah.
it's
Each
not.
model only has a two phase.
Yeah, two phases. Yeah. Yeah, sorry for this confusion. It's actually two models, but both of them have a near state and gapped dimerized phase. Oh, of course, they are different, right? They are different. So now I come to the last cut that we cut here. So this cut exposes a surface with two inequivalent sublattices. So we have this sublattice A and the sublattice B. And this make, because the strong bond in between, which makes this degeneracy of the dangling bonds lifted. So effectively, those two A have effective ferromagnetic topping. So this A sublattice form a ferromagnetic order. But the bond between A and B are still antifermatic. So this B, in B sublattice, we have weaker anti-parallel magnetization. So in the end, this boundary surface, we have this ferry magnetic order in this case. So this can be seen from this plot. So this is the surface magnetization. This is the bulk. This is the surface staggered magnetization. This is the surface uniform magnetization. So yeah, these open symbols are uniform, and the field symbols are staggered. And we can see even at J prime much larger than J, so the phase is actually deep. The bulk is in deep disordered phase. We still see we still see very strong order. And of course, this is a critical. This blue symbol, if the bulk is at critical point, we still see very strong staggered magnetization, and also uniform magnetization. So this shows that the surface is at this ferrimagnetic state.
Are you saying it's because the ferrimagnetic or long-range order is allowed at 0 temperature, while the normal antiferromagnetic order is not allowed?
I think so, yeah. I think so.
Why is the ferromagnetic allowed?
It's like if you have a spin 1/2 ferromagnetic chain, it certainly has order at 0 temperature, but the antiferromagnet does not.
Yeah, if it's just as Anders said, if this the dangling bonds are identical, it's just antiferromagnetic chain, then it's not order, will not order at 0 temperature, 1D chain. But in this case, it's not degenerate.
But then
In between, they have if they have a strong bond. You can think from the SSE, right? You have a very strong bond here. That makes the two spin here effectively ferromagnetic.
So then it's always ordered, even as you increase G.
Yeah.
It's
Yeah.
infinite G. is
Here you
ordered.
see we have quantum critical point, and also G prime much larger than 4J, which is in a deep disordered phase. Here is 2.5. Here is 4. So the bulk doesn't matter. Or I should not say there should be a very strong bond here, right?
I have a question.
Yeah.
If we go to the nail order state, nail order
Oh,
point,
yeah.
this surface ferromagnetic order disappear.
I think so. Then there's all bulk, right, behavior.
Then is it like the first order transition about the surface order?
First order transition.
Even at quantum critical points, surface has very strong orders. Yeah, this figure in this
Here.
Yeah, yes. For example, if the strong correlation, long-range correlation exists,
Yeah.
even at critical points.
Yeah.
But in the nail phase,
Maybe in the null phase, the edge still has some ferromagnetic character.
Yeah, that's,
So the edge must still not be completely antiferromagnetic.
No, I don't know. But for example, when J prime is equals to J, I don't think there's an order, right?
Well, that's a special case, but once they are a little bit different, maybe.
Maybe.
I'm not sure, but
Yeah,
otherwise it's like Harada-san says that the alternative is that the surface undergoes a first order transition, which seems a bit unlikely.
First order.
Because if you say that you have order at the critical point, now if you go slightly in the null phase, what you said is that that order goes away. That means the order jumps, right?
Oh, I don't think it goes away. But when if this degenerate is recovered, it will go
Right.
somewhere, right? But in
But if
between,
you have
it's,
some different bond strengths.
yeah,
it's
that
not
can
really-
be difficult to be studied. Yeah,
I think it's probably easy to study.
yeah. Maybe we should do it. Yeah. Anyway, we can also study the correlation, surface correlation, and the surface bulk correlation. You can see there's long-range order, as Tara-san mentioned, and this is this decays to zero. And we have two exponents found. Oops, always confused. One is eta e, and this eta per e. And these two exponents do not satisfy this simple scaling relation, which works for special and ordinal. So we have no explanation, but apparently that the simple dimension count doesn't work.
Why do you have their parallel? Isn't the surface order?
Yes,
So then why is it inter?
but you still have this. I should say.
It goes to a finite value.
Yeah. Goes to, but you have it's a power law. Yeah, it is a power law.
It's how it approaches the constant.
Yeah.
It's like you have this regular part added in and you study how that approach is approached.
Yeah, there's a constant, but plus a power law.
But isn't it a bit hard to extract that exponent because there could also be corrections on top of that?
Yeah, can be. Yeah. But
So is it exact? Is it possible it's exactly one?
it's possible. It's not exact. We
It's 1.004.
no idea. Same one, right?
What's
Maybe
that?
this one. Yeah.
That's probably one. Right?
Yeah. Very close to one. Yes. So maybe there's a surface order may induce a length scale besides the bulk and the surface correlation length. Yeah. Because this scaling relation we counted because based on there are only two lengths, right? Surface and the bulk relation.
But could it be that that just satisfies mean field theory or something, which is why that thing is
No. This is mean field. Mean field theory satisfies that, but we do not.
How do you know mean field theory satisfies that?
Well,
I see.
some, yeah, mainly eta is zero, and
I mean, I think it may depend how you define it.
people have some calculation.
There's a one.
People have some models to field theory, yeah, mean field calculation of this. It's a scaling dimension, rather general, I would say. But it's strange, we don't really understand what's going on here. Yeah, maybe it's due to the transverse and this longitudinal correlation are different. Oops. So here's my conclusion. We have studied the surface critical behavior of two dimerized Heisenberg models at their bulk critical points. We show all three types of surface critical behavior that are realized with certain surface configuration. And gapped surface states in the bulk disordered phase lead to ordinary transition, and gapless surface states result into a critical special transition, even precluded in the classical model. And we find a very magnetic order on the surface of K2 of the staggered model, which leads to extraordinary transition with surface anomalous dimensions violating scaling relation. So I think I have no time to do the second part. So thank you for your attention.
I have one question, maybe related to Naoki's question, why these anomalous things in the staggered model are not seen, but maybe the last part is exactly that. Could it be that it's very hard to determine both or one of these exponents because of this cubic terms, this new irrelevant field which appears in that model?
In this last extraordinary case?
Because it appears with the staggered model, right?
Yeah, but
Of course, the differences are very big, so I'm not sure if...
yeah, because here, yeah, it's too big to be. I mean, one is critical, one is very magnetic. I don't think there's some relation.
So, may I ask a question? And I'm a little bit confused with the extraordinary transition in your calculation, because as Kawashima-sensei asked the relationship between QCP and the thermal transition, the control parameter in the quantum system corresponds to temperature in this phase diagram, right? So it's okay for ordinary transition, but in the case of extraordinary transition, so if the vertical axis corresponds to the control parameter in quantum system, so we should accept the 3 different phases. So the paramagnetic phase and the intermediate phase where the surface is already ordered, but the bulk hasn't been ordered yet.
Yeah.
And the third phase is both are ordered, right? So
Yeah.
we should expect the 3 different phases.
Yeah.
So therefore we should accept the 3 different quantum phases.
Yeah, but we didn't.
So then why you say that it's an extraordinary transition?
Yeah.
So they're degenerate in that sense, right?
What?
Two lines would be degenerate because there's a surface and the
Oh.
bulk are both somehow ordered or critical, right?
Yeah, but
I'm
we
a
we
bit
don't
confused
have
with the relationship between this phase diagram and the quantum phase transition in your model.
Yeah.
I think there is, but you just didn't study it, right?
Right. We didn't study it. We don't have a adapting parameter here. This classical case, you have a surface.
But I think
Yeah,
you're
but
talking about the vertical
the-
one, right?
Yeah,
If you
but
vary J prime over J, that's
J
you
prime
do that.
over J. Okay. Yeah.
so
In
you
that case,
have only one control parameter in quantum system. right?
yeah. We in that case, we only start the bulk is setting at GC. We didn't move GC at all.
What do you mean?
That means I don't know what is here, what is here. I only know here.
No, I mean that in only for type 2 cut, the changing J prime over J corresponds to changing temperature in classical phase diagram, right?
No.
Well, why not?
Because here we.
This order of phase corresponds to paramagnetic phase in classical phase diagram, right?
Yeah.
So therefore, there's a change in controlling J over J corresponds to controlling temperature in this phase.
Yeah, we didn't change J at all. No change. I mean,
you did a little bit, because at one point you said you sit at the critical point, and another point you sit deep inside the dimerized phase. So you did
in
So that's
only case here we test this boundary, this surface is ordered even when G is inside this high temperature or disordered phase. But in all cases, we don't.
So you have one point in the high temperature phase.
Yeah, only one point. Yeah.
But if you study many values, you can in principle do
Right.
what Sunetsugu-san says.
Yes.
And you should have all these three phases.
Yeah, forget about this this point.
I thought that if you increase the temperature, which is you make G, this thing is always ordered. So it's you never have the paramagnetic phase.
Oh yeah, that's true.
What?
I mean, in the classical model, if
Yeah.
you heat it up enough, at some point the surface is disordered. But I thought here, from what you were showing us, is that even when J prime is equal to 4J, the surface is ordered, and presumably it's ordered even when J prime is infinity.
Yeah.
So it's like that surface ordered phase extends all the way to infinite temperature.
Yeah, but if you want to change the state, you have to change the coupling, right? Along this surface.
Yeah, if you also change the surface.
Yeah, if you change the coupling in this surface, you may have some classical behavior, similarity. Yeah.
But anyway, you need additional the control.
Yeah. Additional parameter to adapt. Here we don't adapt any parameter.
It's conceivable that this thing will be ordered as long as you maintain this symmetry, no matter how you terminate it. Like no matter what you do to the, it's like the ferromagnet is always ordered.
Well, but you could make the edge go into VBS state or something like that, right? If you choose the couplings.
Yeah, you maybe you change this this be stronger, this weaker, stronger, weaker. Right?
Oh, if
you
you
can
break-
adopt that.
You're
Right?
saying you break a symmetry that I think it may be possible that if you have a particular, you enforce the symmetry which your edge has,
Yeah.
then even if you modify the Hamiltonian, it will still be.
But if you make it a JQ, chain,
Yeah,
it
yeah.
can, or J1.
Okay, yeah. You have to you have to adapt it. For example, this model you have to adapt the J prime and the J, the ratio. You have to introduce a new parameter. Right? But here, I mean, engineering that we don't do that.
But maybe it's difficult, like Ryuko says, because sublattices A and B are always different, right?
Yeah, there may be something.
So maybe it's not so
Okay.
easy to get rid of this ferry order.
Yeah, I think there may be something.
Yeah.
I mean, you could tune to some special point where you get a wave.
Yeah, that's maybe we can study how to tune the surface Hamiltonian, right, to reach certain state.
But for your argument, I think it's not important because you have the two low T phases. That's enough for your argument to study what you want to study.
Yeah. We just that's the point, that right, because we don't want to adapt any parameters. We just cut. That's the point.
So it's very generic.
If we adapt in some parameters, then it's just a classical mimics, right? That's not good. Not the point, I should say.
Question? Is it possible to see the extraordinary transition in the columnar case?
In what?
In the columnar case, not the staggered case,
Oh,
but by having a zigzag.
Yeah, maybe you could try cut some other way, right?
Yeah.
Yeah, but we didn't try that. Yeah, or zigzag, you break some certain configuration.
Maybe it would be nice to do because you have this discrepancy. Maybe it would be nice to see if you have some other case if you get the same exponents.
Yeah. Yeah, good. Yeah.
Let's start the speak again.